Hi everyone, my name is Albert Rapp, and in this video I want to show you how you can create more versatile functions using R. So what I mean by that is that I want to show you how you can write your own functions for which you do not necessarily know at the beginning how many arguments they have and what the argument names are. So let's make this more precise. Let us take a look at these two data sets I call dat A and dat B. To show you what we want to get in the end. So we want to write a function that can create both of these data sets that are similar, but they are not exactly the same, so we cannot hard code the stuff like the column names or anything like that into the function that is supposed to create both data sets. So let's take a look. So this here is dat A, and as you can see already, we have a different amount of columns in this data set. So dat A contains columns mu and sigma, and dat B contains only a column lambda, but both of them contain a column dat. And here is already the first difference. If we want to have a function that can create both of these data sets, we will need to be able to pass both mu and sigma or lambda to this function in order for this function to create these specific columns. Also, there is this column dat, as I just said. So let's look at this list-like column more precisely. I will use the plug function to take a look at the first element in both of these data sets. So as you can see here, in dat A, the first data set in this list-like column, dat contains two columns n and proc mean, whereas the second data set contains the column n and proc variance. So the logic behind this, or the logic that I implemented to create this data set, is that in each entry of this list-like column, we will simulate a stochastic process, or in this case we make it really easy. We will create realizations from random realizations from R norm, for instance. So from R norm, we'll simply call R norm here, and mean will be mu, the standard deviation will be sigma, and then we compute, in the first case, we compute for each process that we generate, we compute the mean, whereas in this second version, for each process that we create, we compute the variance, and in this second case, we will use rexp for the generation of the random variables. So this is in the end what our function is supposed to do. And again, we want to have one function that can do both, simulate normal variables or exponential variables. So Rx would simulate realizations from the exponential distribution, and then summarize the realizations by computing either the mean or the variance. And if we have a function that can do both, we can actually make this technically way more complicated by letting it simulate something completely different, calling I don't know, some other simulation function instead of R norm or Rx. And we can also could technically use a different summary function like median or something we have created on our own, whatever it is that we need for our summary. So in the sense, these two data sets, dat A and dat B, are different because they contain different columns, but the logic that creates them is the same. We will first take parameters. In the case A, we'll take the parameters mu and sigma, use them to simulate random numbers, and then summarize them. In dat B, we do exactly the same thing, but we just take only one parameter, lambda, instead of two parameters, and then we summarize it differently. But again, the overall logic is the same, and we want to be able to write a function that can follow that logic, but is not restricted to hard code stuff like the simulating normal variables or simulating exponential variables, or summarizing by taking the mean or by computing the variance. Okay, so for that we will need two simple concepts, and the first one is called dot dot dot. At least it's pronounced that way. Written it's simply like dot dot dot. You have probably used it implicitly if you've used the tidyverse. You've used it a lot by using the select function. If you look at the select function from the tidyverse, if you look into the documentation, you will see that the two arguments of that function are actually only the data argument and this dot dot dot. So let's see what this dot 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 does if we try to write our own select functions. So let's call this mySelect, and we will simply try to select two columns from this famous iris data set. If you don't know it, it looks like this. It's a standard data set that comes pre-installed with R. So you probably have seen it already, but for those of you who haven't, here it is again. And let us simply write a function that can select two columns from this data set, or at least let's try to code a function that can do that. So even if we would use the dplyr select function, so this tidyverse function, to pass x and y along to select like this, we could think if we intuitively this should work, because we just take x and y and throw to select, and we already know that with select we can simply call it call this function like this. So if we want to get, for instance, the length and the width, then we could simply call select. And technically you could think that mySelect, if I'm taking mySelect, it will work exactly the same, and we can simply even leave out the iris data set, because we have hard coded in here that we're using the iris data set anyway. But if we do that, we'll immediately get an error which says that it isn't found. Okay, this is still in German, but don't worry, I will translate the errors. In any case, it will say that it couldn't find this variable here. And the problem with that is that because it will, the R will try to find this variable in our environment, but what you can see in this environment here is that of course this variable is not available. And the point of this dot 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 operator, which is what select uses to avoid this problem, is that this operator simply takes everything you throw at it and then evaluates it at a later point. And this is exactly what select does. It evaluates it once it has become clear that we're taking variables from this data set iris. Because in iris, in this data set, these variables obviously are available because they are part of this data set. And we can technically use exactly the same thing by also using this dot 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 operator. So instead of using specific arguments here, we could simply replace this by these dots, and then we have to replace it in here. So we will know that everything we throw into our mySelect function will be caught by this dot 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 and will be plugged into at this position, and because select implemented it with dot 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 as well, it will be carried along until we can actually evaluate what we want. See, here you see that we can actually get the result we intended to, and it all worked by using this dot 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 operator to pass the variables along until we can finally evaluate it. And this is something we will need for our function later on to simulate the corresponding variables, because we don't necessarily know which function we use for simulation. So it might only take one variable, one parameter for simulation as the exponential distribution does, because it only takes the rate parameter lambda. Or if we want to use the R-norm function, we will need both parameters mu and sigma, and we could think of something else which might take 3, 4, or 5 parameters, and all of that can be handled by the dot 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 operator, because it can handle arbitrarily many arguments which do not necessarily need to be named at first, and will be just dragged along until we use it at some point. And this will be useful for the simulation part. And what we want to do later on is to summarize, right? But what we want to do is to be able to use different summary functions. So in this first case, we use the mean. In the second case, we use the variance. And notice that the column name also is different every time. So we will need to have something that have an argument that can where we can input our column name here, and also where we can specify which function to use. And this is something we can use with dot dot dot, of course, but we could also use curly curly, which is pronounced as curly curly but is written as these two curly brackets, and is works similar to dot 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 in the sense that it allows for later evaluation, but it's more tailored to only one variable instead of multiple variables. So let's see this in action. Let's try to write a select and add function that basically does the same thing as we've done here. Select a column from the iris data set and then compute an additional column after we've selected this a different column, and name it by some variable we've selected before. So let's call this select and add. This will be a function that will only select one column X, and it will later on name the column that we add will be named Y, whatever we pass to these arguments. And then this syntax is pretty similar, or technically similar, but it's quite easy. Is that whatever needs to be evaluated later on, which is X, for instance, needs to be wrapped into these two curly curly brackets, and then everything just works fine, and we can simply code everything else as we normally would. And if we wanted to add another column, for instance, we would simply use the mutate function, and then we said everything that is variable in the end needs to be put into the curly curly brackets. So this is what we do here, and then we simply say what we want to compute in this column. Let's just add a number 5 to everything. The only special thing you have to worry about here is that the standard syntax does not work in this case. The one thing we have to add is a colon here. Technically, I don't know why we have to do it, and it's just the way the syntax works. But just be sure that you add this colon, otherwise it won't work. Whenever you want to name a column by a variable name, you will have to use this colon here. And then we can simply use this function. Let us select the width again, and let's name this, I don't know, super cool name. I have to compile everything. Yeah, and then it'll work just fine. Technically, it should also work like this. We don't even need to make sure that's the string here. I'm not entirely sure if we need it here as well. Let's check. See, we don't even need it here. That is because, now that I think about it, it should be because everything that is, it works similar as to dot dot dot. Everything that is thrown in there will probably be evaluated later on or converted to something. That is actually, that simply works. All right, these are the two basic ingredients we will need. One thing which is not, it's probably known to a lot of you, but I should mention it anyway, is that functional programming. I wanted to skip it in this video, but whatever. Functional programming, let's review that in this video here as well. The point of functional programming is that we can use functions as arguments for other functions. So for instance, if I want to write a function mySimulate that will simply simulate n random variables from, say, the random normal variables. So if I simply want to use this functions or possibly the rexp instead, I can simply use func here and then call n. So what this does in the end then is that I can call this my new function, say that I want to have 5 realizations, and then I need to say from what distribution, and I want to use the normal distribution, so I will need to use rnorm as argument. Notice that I do not pass rnorm with these parentheses here, because that would call rnorm, the function. No, I want to take this function and pass it along to the other function, and this will simply be used then here as this. So basically this is just a wrapper function around whatever I pass here. So what this my new function does is simply would call rnorm here with this argument n. If I use rexp here, it will simply take this and plug it in here. This is the logic behind this. So this is the most basic functionality in functional programming, is that we can use functions as arguments for other functions as well. And this will be helpful for our simulation function as well, because then we do not have to hard code the simulation function into our new function, because we can simply use this function name and pass it along, and then it will be used appropriately. Okay, these are all the ingredients we need for our simulation purposes. So let's try to start with the simulation part. I will call this new functions simulate and summarize proc. So it will simulate and summarize processes. So it will be a function that uses ... I simply put it at the first position, so I know that all of my parameters that are used for the simulations are just the named parameters at the beginning of this function call. Then I want to know how long each realization of my process is, so how many random numbers do I want to create, so how many so how long should a sequence be. For instance, I could say I want to simulate 200 numbers, random numbers, and then I will also need to specify how often I want to do it. Because as you've seen in this data set before, we have simulated 5 times random numbers, and then for each time we have computed, in this case, the mean here. So this n will be handled by nSimUse here by this variable. And then of course we will need a function that does the simulation part for us. So the only thing we need basically is to, first of all, I only want to implement this functionality here. So this here is implemented by the simulate and summarize procedure. So what I want is that I generate a table that has columns t, the columns n. This will just be again the number of the realization, and then we'll just call it value, and this is where the random numbers will be stored in. And I simply do this by simply calling this simulation function here with the appropriate arguments by using the pmap function that will use the an args list variable that will in the end come from this dot dot dot, and then it will simply use all the parameters with this function I have passed to it and then simulate all the numbers I need. So this is what I want in the end. So I will need to be able to somehow create this variable args list from what is passed to the to this dot 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 operator. And also one thing that I will need every time is that's independent from this dot 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 operator is the numbers of realizations, the numbers of random numbers that are supposed to be created. This will always be tmax, and then all the other parameters will simply be passed along via this dot 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 operator. So let's see how this works. I will set a seed so that my random numbers will always be the same, and then I can simply call my function. And I want to simulate random normal variables, so I will need to specify the mean argument and the standard deviation argument. So let's say mean is equal to 1 and the standard deviation argument is equal to 2. Let's say that tmax is 200 each times, and we want to have everything done 3 times. I think in our original example we had it 5 times, so let's do 5. And my simulation function that does the simulation for me is, as I just said, rnorm. And again, it uses the arguments n, mean, and sd. Mean and sd is given by this function call, and n is hard-coded into this function because I know that all my functions that I want to use, rnorm or rx, for instance, they always have this argument n, so I hard-coded it. Technically, you could also leave that out as well and make that a variable. But in this case, I decided to make this, to hard-code this. So let's see, simulation function, not simulate func. And what did go wrong? Of course, I forgot to make sure that the lengths are the same. I need to make sure that the numbers of parameters, since I only pass one of them, but I want to have in the end have everything 5 times, I will need to make sure to repeat everything multiple times. Okay, this is still not working. Let's see. Simulation. Yeah, of course, mean and standard deviation are not parameters of Rx, which is rnorm. And this is in the end what I have in what I get as a result. So as you can see, this does exactly what I want. I have now, in each case, I have 200 realizations, so I have tmax realizations from a normal distribution with mean 1 and standard deviation 2. Maybe we should check what is going on here, so why I added this. This is probably the only tricky part in this simulation, because here everything else just take the parameters, throw it to the function via the mapping function, and everything else worked out fine. Technically, I added this t argument, but we don't even need it, so let's get rid of it. In the end, our summary function doesn't even use it. If we want to also implement something with time dependence, we could put in this t back again, but here it doesn't matter. So let's see what I did with this list here and this repetition. So say I have exactly the arguments that I need for my random normal distribution, or for my R norm function, n, mean, and SD. And I want to call this function R norm 5 times, because I want to have 5 realizations. So 5 times 200, I want to have that many realizations. Then I will need to have a list that contains each parameter, triple in this case, 5 times. So I will need to repeat everything 5 times. If I simply pass this along to the repeat function and say repeat 5 times, then everything will be mixed. It will be n mean SD and then n mean SD again, which is not what we want, because what we want is simply want to have a list consisting of 3 sublists, and in each sublist each parameter is repeated 5 times. And this is simply done by using the map. And in the end, this is then what will be passed to this simulation function. Alright, so this is we've already got the simulation part covered. Now the only thing we need to do again is to summarize these, because what we want in the end is to have a number here, which is supposed to be a summary statistic, and not a list-like columns with consisting of vectors of length 200. So let's implement that as well. And what we need for that are 2 additional functions, 2 additional arguments, namely a summary function or a summary name, because as we've seen here, this is an individual name, so we'll need a variable that covers that, and we need a function that actually does the summarizing for us. Okay, so this is what we need. The only thing that we need to add to this, to our previous code, is simply, this is the current result, we unnest this value column. Then we get something like this, and then we can simply group by n. And then we summarize as we normally would. And then we use the curly syntax as we have done here. So simply this variable that is supposed to be the name put into the curly brackets, colon and equal sign, and then the function or the result that is supposed to be in that specific column. So let's do that. So instead of y, we have a summary name here now. And what is supposed to be computed? Well, the summary function is supposed to be used on this column values. So let's do that. Let's see. So summary name, let's call this my mean, as we did in the previous, in the original example. And of course, the summary function then is supposed to be the mean functions. Again, see that I don't use the parentheses here. I simply take the function and pass it along as an argument, same as I did with R norm here. And if I'm doing this now, then you see that we get exactly a result that is in the same format as in here. So now we have a function that can create and can simulate and summarize a stochastic process based on an arbitrary amount of parameters, and the resulting column names can also be, or the column names can be chosen, and the used summary statistic is versatile as well. So we've implemented this, how to compute one specific tibble here, and then we simply need to map this over all the possible parameter pairs we have here. So let's do that as well as a final step. We don't need this part here anymore. Let's create that A, by simply using expand grid to get a grid of the parameters. So in this case, we want to have mu range from -1 to 1 by 0.25 steps, and we want to have sigma ranging from 1 to 3 by 0.5 steps. So that A will now look as we've seen before. Of course, the that column is missing, and this part we simply add by using our previous function in conjunction with the map function. So we want to pass mu and sigma to this function, and then call this here. So the mean is supposed to be x now, and the standard deviation is to be y now. So x is mu, y is sigma. And once we do that, we get exactly what we had before, or what we wanted to create. And as we have seen now, this is quite versatile because we are not restricted to these parameters. We can simply say, okay, now let's look at not normal distributions, but exponential distributions. Let's call that parameter lambda. Let's make it range from 0.5 to 1.5. And then, of course, we don't need two mapping arguments. Can get rid of that. The mean, not the mean, the rate is supposed to be lambda. And I believe in the second example we didn't use the mean, but the variance. Yes, we wanted to use the variance as standard, as summary statistics. So let's do that here. So variance and var is supposed to be used here. So this is supposed to be that B. I have missed something. Of course, rate is not to be fixed. It needs to be. I forgot to change this here as well. Now it's working, and now we have exactly what we intended to create. So alright, that's that. We have seen how we can create versatile functions using the ... operator and the curly operator. Of course, this example is very simple, but the strategy on how to create versatile function is the same regardless of the complexity. As I've said before, we could here change the simulations function to something completely different, something which is more complicated, and the summary statistic could be arbitrary as well. So there is not necessarily a limit on the complicated stuff we can do here, but the mechanism of how to achieve that is the same and works by using this ... operator or curly. So with that, I conclude this short video. I hope you've learned something. If you want to code along, feel free to check out the corresponding blog post where all the code is, where you can see everything again. So there's the code, all of my explanations, and yeah, I hope that was helpful to you, and then I will see you in the next video. Bye.